Hello everyone. I decided to make a video to show the pipeline from Slicer2Kwave for your reference. The first thing I will talk about is that this code is available on GitHub. So here it is on my GitHub repository with scripts. The main one is Slicer2Kwave. As I update this, you'll be able to see the code. So that's one perk of having it on GitHub. But the main perk, I think, is that if you want to use this approach and merge it with the optical tracking methods that you develop, then you could create a new branch off of this repository and edit my scripts and add your own scripts. And then, I'll be developing these independently, but once they're both in a stable position, we can merge them using the GitHub tools. So that would be ideal. Sounds challenging, but I think that's how it's supposed to be done in theory. So, okay, let's do this. So here in Slicer, I have two things loaded. One is a transducer mask in the form of a nifty file, and that's what's shown here. There's a script inside this repository that takes the KWAVE functions that make transducers and turns them into a nifty file. The other thing I have loaded is a CT dataset. So here it is. It's weird that you can't see all three of these right now. There we go. Okay, so we want to place the transducer relative to the CT now. So I like to do this with the 3D viewer. You could probably do it down here as well. But to get the transducer to show up as a 3D object, you go to volume rendering and you select the transducer mask and you hit the little eyeball. And now there it is, looking good. So we need to just place this in a position that we would like to simulate. And if you had this like labeled in the CT volume or in an MR volume, you could just, I actually haven't developed that method yet, but I'm sure there are ways to like make the focus align with whatever target you select that aren't manual. But for now, we're just going to arbitrarily move this transducer around. So to do that, you create a new transformation. Create new linear transform as, name it whatever. And you need to scroll down and make the transducer transformable. So move it over there. Now we can just move this guy around. So these are the rotation options. Oh, my computer is slow right now. I think the Zoom recording is making this very laggy. Oh yeah, they're probably sharing the graphics card. Okay, and we'll move this over here. That looks good enough. So now we need to decide what do we want to simulate, like what extent, and how do we want this to be sampled. And there are a lot of ways to do this. The one way to do this is to crop the volume. So you come down here and you say crop volume, and there's some, see this box, you can shape this box to be whatever size you want. So you'd want that to include the transducer and the CT that you're interested in. And nice thing about this approach is that you can set the resolution of the volumes. So you just use this spacing scale, and like you can see the transducer. Let's see. Okay, so we're looking at cropping the CT volume here. So the CT volume is 1 millimeter voxels, but say we wanted to simulate 0.25 millimeter voxels, we would have this scale factor You set the 0.25, which converts the 1 to a 0.25. You know, 0.2. But so that's one way, and you would use this mask to crop both the CT and the H101 nifty. But the way that I think is easiest for these single element transducers is to actually resample the CT volume using the transducer mask. So I'm just going to hide this ROI for now, and we're going to do it this way. So you go registration, resample image, and we want to resample the CT using the H101. Oh, and before we can do this, we need to harden the transformation that is moving the transducer around right now, so that the CT gets resampled with the transformed transducer, as opposed to being resampled where the transducer was initially loaded in, which was like somewhere down here. So to harden the transformation that is being applied to the transducer, we go data, transformation hierarchy. Here's the transform. You can see this is inside of the transform, so it's being applied. If we right click, harden transform, this now moves outside of the transform. And so now it's built into the ITK structure that's representing it. And so yeah, now we can go back to our resample images. H101, no, we want the CT to be warped. The reference image is the H101. We'll create a new volume output image. We'll call this CT sim space, because this will be the CT data that is loaded into the MATLAB script. Oh, advanced options. I don't think we need to set anything else here. Interpolation modes, you know, data type, some nice options. So we'll just hit apply. It's taking a while because it's upsampling the CT to match the resolution of the transducer. So now you can see that we just have a CT file, which is the same as the extent of the transducer. And so we'll go with this for now. But say you wanted to actually simulate like way past the focus, you could either edit the transducer script that makes the transducer, or you could use the crop volume feature to make this transducer even bigger. You know, you could arbitrarily shape the transducer file to be as big as you want and simulate as much as you want. So for now, we'll just call this good. So we need to save the data to the disk. And the only thing that we actually need to save is the resampled CT. So this is called, we call this CT sim space. We'll save this as a compressed nifty. Change the directory. Save. Okay. So now, let's see what's next on the outline. Save to disk, run MATLAB script. So let's look at the MATLAB script. Oh, let's look at it here. So this MATLAB script is going to load in the CT sim space nifty. It's going to load in the H101 file, and you know, you need to set these to whatever you use. So in our case, this will actually be .nii.gz, and this will be H101. I think I named it upsampled. And there are just a few inputs that you can set here. So most of the things that you set are in this top section. this checks to make sure that the CT sim space and the transducer mask are the same size they need to be for the script. You'll notice the script is only 60 lines long. It's not much. The most complicated thing that the script does is pad the matrices so that one, there is room for the perfectly matched layer, and two, the matrix geometry ends up being something with the low prime factors for the computational efficiency. And so that's all handled here. This will output like the factors that work with your inputs, and then you can select the ones that you like here. Just input numbers that come from the check factors output, and then it'll appropriately pad the geometry. There's a function here, get acoustic properties. This just takes CT data and outputs the medium speed of sound speed and the medium density. And then, generate the KWAVE grid, create a continuous wave signal, and you run this. So I'm gonna pause the recording here, and I'll actually run this on the server because my computer can't do this. And then we'll start back up and I'll load it back into Slicer, and that'll be it. So, okay, so we're back, and I ran the MATLAB simulation on the server, which writes the results of KWAVE out into a Nifty using the header or the metadata from the transducer Nifty. So it like assigns the KWAVE output to a new volume, but gives it all the properties of the transducer Nifty. And so then I transferred that back to my computer. And so let's load it in and see what it looks like. KWAVE output is what I called it. Okay, so it's over here. So to make it line up with the transducer, oh, and the data is in here. There's a few things I'm confused about right now. I think this is partially due to switching to the new KWAVE library. I don't know why the transducer is in this output. That's new. But so to make this line up with the transducer and with like the CT or the MRI that you load in, you just need to take the KWAVE output and put it inside of there, and there it is. So let's do an overlay for like final visualization. So what we'll do is we'll make the KWAVE pressure look red, and we'll overlay that on some CT. Ooh, these do not look lined up. Oh, there we go. Right, let's do this. Volumes, pick the KWAVE output. We'll make it red. There it is. So what we wanted. I don't know if this is right. I think it's right. Yeah. All right, there it is. So that is the general process. It's still under development, but I think that gives a picture of the steps that are taken, and also probably the areas where it can be improved. All right, that's it.